Hi everybody, welcome back. In this episode we're going to talk about neural networks, and we're going to see how to write a neural network from scratch in Java. If you saw some of my previous videos, you know that I have written the snake game in Java, but it's controlled by a human. So in this series of videos I will implement a neural network and a genetic algorithm so we can then let the computer gain control over the snake and learn from a generation to another and see how well it does into playing the snake game. But in order to do that, first we need to implement a neural network. So let's see how we do this. I started by looking up a lot of videos and doing a lot of research about the neural networks. And I found a lot of material out there, but it only shows how a neural network works and how it performs. And it's basically just a demo in the video. So I'm trying now to see how to actually build one, how to build one from scratch, how to make a genetic algorithm on top of this neural network. So in order to do that, let's start with just some theory. And one of the best videos I found about looking at the concepts of a neural network is this one from 3 Blue 1 Brown. It's called "But What is a Neural Network?" in Chapter 1, Deep Learning. And he makes a perfect explanation of how neural networks work, what they mean, and how to be implemented. So I definitely recommend that you watch the video. I link it in the description to get a better understanding of the neural network, better than I can explain it myself. But in essence, for a neural network, we can consider it as having different layers. It has an input layer formed of multiple neurons. It has a couple of hidden layers also formed of neurons. And finally, it has an output layer. What is interesting for us to understand is that each of the input can have a certain value. So each neuron in the input can have a certain value. Then something will happen in the middle of the neural network, in the hidden layers. And based on a configuration of inputs, then there will be a configuration of outputs that will be activated. So in our case, one of the neurons in the output layer will be activated. Namely, we're going to take the neuron with the highest value in the output layer, and we're going to consider that one as being active. Now, this neural network is a fully connected forward-feeding neural network. What does this mean? For short, it's fully connected, meaning that every neuron in a certain layer is directly connected to every neuron in the adjacent layer. And it's forward feeding, meaning that there are no cycles in this network. Each neuron is connected to the next neuron in the next layer, and there are no connections coming back from a layer to another. Another key concept of a neural network is that each connection between two neurons, for example, from this neuron into the second layer and this neuron, the connection itself has a certain value. We're going to call that the weight of the connection. And as I said, all neurons are connected to all neurons in the next layer, so we're going to have a lot of weights in here. Furthermore, each hidden layer will have a bias array, and this bias array is also an array of numbers, each neuron corresponding to a certain value in that array. We're going to see how this is used in a second. The inputs of a neural network could be anything, could be any number, but typically I'll try to keep them close to 1. The weights are initialized with random numbers in the beginning, from -1 to 1. And each neuron will have a certain value as it is calculated based on a certain input. The value of each neuron is called the activation of that neuron. When a certain input is applied into a neural network, we need to calculate what are the activated neurons in all the layers, basically in the hidden layers as well as in the output layer. So in order to do this, what we basically need to do is multiply matrices. For short, even shorter than that, we're trying to calculate a weighted sum between the activation neuron multiplied by the weight of that connection into the next layer, and then we do this for all the neurons and for all the weights between the two layers. Once we have calculated all this weighted sum, then we basically have calculated the activations of the next layer. And we continue doing this layer by layer until in the end we find the activations of the output layer. The values of each individual neuron, basically the value of this weighted sum, could be a number between different values. We don't know between which range will be. So we need to somehow squish this number to a interval that we are interested in. Typically, this is done by using an activation function, which will squish that neuron value to either -1 interval or to a 0 to 1 interval, depending on different needs. This activation function could be something for like this sigmoid function, or it could be a ReLU, a rectified linear unit, which basically just takes the number itself if it's positive or 0 otherwise. One more concept here is about the bias of a particular network. Each neuron can have a bias, so then when we perform the weighted sum, we don't want always to activate, or we only want it to activate after it reaches a certain threshold. We can call that threshold a bias, and we add it to the weighted sum before we call the activation function. So eventually, after we have our neural network, after we have all the weights and the biases, when we calculate the output of a neural network, all we need to do is basically calculate some weighted sums, perform what are called matrix multiplications, add the bias to that matrix multiplication, and in the end we have the output layer. All right, so let's see how we implement a neural network now in Java. Based on the concepts that were presented, I implemented two classes basically. One is the neural network, and it's the hidden layer. In the neural network, the important things are the hidden layers are basically an array of hidden layer objects, and this is the number of hidden layers. This is the number of items we'll have in this array. And the activations is basically a bidimensional array of doubles. These are the values of each neuron in each layer, basically. So the first value in the activations will be the layer, 0 being the input, 1 being the first hidden layer, 2 being the second hidden layer, and so on. And the last activation layer will be the output layer. And then the second dimension will be the individual neuron in that layer. So when we create a neural network, we give just the number of dimensions. For example, like this, neural network of 432, it means it has 4 neurons in the input layer, 3 neurons in the hidden layer, and 2 neurons in the output layer. If I would put here 432, then basically it will be 4 neurons in the input layer, 3 neurons in the hidden layer, another hidden layer with 3 neurons, and an output layer with 2 neurons. In the beginning, what we do is basically just dimension the arrays and create the double array for the layers.length. This is the activation number of layers. And then we create the hidden layers, which is basically we have as many hidden layers as we have the number of layers here, -1. Interesting to note is that the output is also considered a hidden layer here, or the output also has a hidden layer, so it has weights and biases. And then basically we just create the arrays, and we allocate the sizes for each of the hidden layers. A hidden layer is basically considered to be the connection between two activation layers. One, it's basically the number of neurons in the current layer and the number of neurons in the previous layer, the one in front of it. Then I'm defining here a copy constructor in case we need to copy a particular neural network into another one. Then basically we just copy each property from the other network into the current network. In this case, I consider the other network to be already initialized, so it has some meaningful weights and biases, so those are also copied when the hidden layers are being copied. In this situation, this happens here. Otherwise, the value for the activation layer are left empty. We don't actually copy the values of those activations. In case we want to load the neural network from a file, then I'm using this utility here, which is an XML serializer that reads from a file a particular object and reads it from there. A neural network on a file looks like this. It's basically just XML representation of the neural network objects with the hidden layers and the activations and so on. Next, we have the process method, which basically just implies that we have a array of inputs that we want to apply to this neural network and see what the outputs are. So for this, indeed, what we need to do is perform a bunch of matrix multiplications and to add the bias, and that will calculate our outputs. First and foremost, we copy the inputs array into the activations matrix on layer 0. So basically this is the activations on the inputs. And then for each other hidden layer in between, we're going to calculate the activations of that layer as being the hidden layers multiplied by the activations behind it. So it's feeding forward from activation I into activation of I plus 1. Once we have the hidden layers multiplied and the bias created, and we have all this activation layer ready, then we're going to apply this activation function, be it either the Sigmoid or the ReLU. So the values are being normalized into a specific interval. We can either use a rectifier function for activation or a sigmoid function for activation. It doesn't really matter, and I'm not sure why would you use one or the other, but apparently the ReLU works a little bit better. So on the activation array here, if we use a ReLU, then basically we just calculate it as maximum between 0 and the activation itself. So if it's greater than 0, it is activation itself. Otherwise, if it's negative, it stays at 0. Otherwise, we can use the sigmoid activation function, which basically just calculates 1 over 1 plus e at the power of minus x. The other class that is interesting for us is the hidden layer class, where we have the weights and biases. These are basically the bidimensional array of doubles representing the weights and a single dimension array for the biases. The weights basically are defined as the weights between two neurons in adjacent layers. So we need to initialize the hidden layer with the current layer size and the previous layer size, And this basically will be the dimensions of the weights array. The biases are only relevant to the current layer, so we have one bias per each neuron in the current layer. Once we create a hidden layer, then we need to initialize it, and typically we do this with some random values. The random values are here in the random for each weight in this weights array. We're going to assign a random value between -1 and 1. Basically, this is math.random gives us a number between 0 and 1. 2 times that is between 0 and 2. -1 is going to be between -1 and 1. We do exactly the same thing for the biases. We initialize each bias with a random value between -1 and 1. The other constructor is a copy constructor, which basically means we're going to take another hidden layer and copy all the values and weights and biases from the other hidden layer into the current one. And basically we just copy values around. We initialize the weights and the biases arrays to the sizes from the other array, from the other hidden layer. And then we just copy the values over from the other biases into the biases from the other weights into the current weights. Then the interesting method here is basically the multiply and add bias. This is a bit tricky because, as I said, we're doing matrices multiplications, and once we have the matrices multiplied, then we add the bias. This is the formula we're talking about. We have the weights matrix, and then we have the activation column. And then what we need to do is calculate the multiplication between this matrix and this column, which in the end will be a column itself. That happens in this particular part. We have the results, which is an array of doubles. Then we create a sum for each neuron in the result. And then we just add up the weighted sum, basically the activation times the weight of that at that location. Once we have the sum, the weighted sum, then we add the actual bias at the end. So this is the sum plus the biases, so that's why it's multiplying two matrices and adding the bias at the end. The result at position I, the position of that neuron basically, is then the sum. If we then look at the neural network, this activations that we create here, which is the multiplication and add bias, is the one that then becomes activated through this ReLU or Sigmoid functions. And basically that's about it. There are no more logic in here. As I said, this is only a feed-forward network. It doesn't do any recurrent or step-backs or cycles. And also in this network, I have not implemented a backward propagation. This means this network will only compute whatever you give it in the input. It will not actually it's not trainable. You cannot change the values or the weights or the biases. That one, for that I will dedicate a special video because that entire process is quite challenging. So to keep this video here manageable in time and size, I will not implement it here. What I can show you here is basically this test function. Test the method where we create a neural network of 4 neurons in the input, 1 hidden layer of 3 neurons, and 1 output layer of 2 neurons. And basically then we just create some inputs in there, and we just push in the inputs through the network by doing this neural network.process, and we just output the values of the neural network. If we run this, then basically this is what its output here. As I said, the values, the hidden layer values, the weights and biases are initialized randomly, and they do not change. They stay the same for the duration of this, because this network does not learn. But as we apply inputs on the first layer, those inputs are being propagated to the output. Now I'm only outputting values which are not zero. If the value is zero in here, I will not output it. So if the value of the neuron in a certain layer is zero, then I'm not, or negative, I'm not outputting it. And basically for each output, for each input, we have this value. So this is just the way the network is functioning. That's all I have for today. In the next video, I'll show you how I'm implementing the genetic algorithm to make this network learn how to play the snake game. But until then, bye-bye.